So I should start. Yeah. All right, welcome everybody to today's session. So it's a pleasure to introduce Jacques Smulevici from Sorbonne University, and he will talk about stationary Vlasov fields on Schwarzschild.
Well, thank you very much, Mihalis. Thanks to all the organizers. I'm very happy to be here. I have to say that hearing some of the previous talks, already yesterday, sort of reminded me of the last time I was here. It comforted me a little bit about the talk I gave, because the topic was holography in ADS, and I talk about the stability of Minkowski space with Vlasov matter. Anyway. So the talk will be about some joint work, which is work in progress, with Renato, but also Boris from Imperial College. And well, I am, I can redeem myself because this time I will be able to stick to the topic a bit better, because there will be a black hole since I will talk about Schwarzschild. Okay, it will be a fixed Schwarzschild because I will talk about just the linear Vlasov equation on Schwarzschild. Okay, and the energy tensors of such fields, etc. So to remind you quickly, okay, so Schwarzschild, let's call it. So I will only look at the exterior. Okay, you can just think of the standard θ coordinates for the exterior. That will be enough for what I want to talk about. Let's call the exterior, let's say, I don't know, mx, and then G sub m for the metric of Schwarzschild. M is the mass. Okay, so let me briefly remind you of what the Vlasov field is. So F will be the main unknown. It's like it's a distribution function. So distribution function. So it's a map from so-called mass shell to, let's say, R plus. The sign will play no role in what I will say. And then P, what is P, this mass shell? It's a set of all points in the tangent bundle, such that X will be here just in the exterior, because I will only look at the exterior. And then P is a future directed and normalized to -1. Okay. And then, I mean, I will, of course, look at the energy momentum tensor generated by such F. So this will be P mu nu of F, okay? It's given by an integral where you just sum up all contribution at a fixed x, at all p's, okay? So it's an integral of F. You look at the fiber in P at each point x, and then you integrate this with two moments, so P mu, PV. And then there is a volume form. But okay, for practical purpose here, at every point x, okay, because of these relations, you can parameterize any such p just by these, like the spatial part of p. So you can write this as an integral of, let's say, R3 in p of f. This would be at the point x, okay, of xp, p mu, p mean. Then there will be a volume form, p, let's say, p1, p2, p3 over, so p naught is positive, but p naught downstairs is negative. So that would be the volume form. Okay. So finally, our F will be required to verify the PDE. So the Vlasov equation will be such that F is constant along time-like geodesics. Okay, and if you write this in, let's say, local coordinates, that looks like this. T P gamma F. Now I have a little bit of material about the geodesic flow and other things on Schwarzschild to introduce. So I thought that in order to keep you motivated, I should start with the punchline and then I'll introduce the material, okay? So the punchline is the following. I will try to convince you that there exists smooth, compactly supported initial data, let's say F naught, let's say at t equals 0, at t equals 0, for let's call this V, let's say Vlasov, for V, such that if you consider F the solution arising from F naught, then you can look at its energy momentum tensor. Okay, so that's a priori dynamical quantity. And the claim will be that, at least in a pointwise sense, with even quantitative rate, this this is there exists, so it's not necessarily for all. Okay, I'm not saying that. But you can construct such a priori completely regular initial data so that the limit of the energy momentum tensor in time converge to an energy momentum tensor of a stationary solution to the Vlasov equation. So here stationary Vlasov will mean that okay, it solves V and dt of F is equal to F stationary is equal to 0. Okay. Well, this is maybe not so surprising that this can happen, but what maybe less intuitive is that this T station of this stationary state will be not smooth. Okay, so there is in the evolution a lack of smoothness that can occur, and I found that an interesting fact. And of course, for this to be occur, because T is a functional that take a Vlasov fields and give me a function. This is a smooth operator a priori. So the only way this can occur is that F stat also will be not smooth. And it will also, it is a solution, huh? So it's not like a lack of compactness or anything like that. Okay, so this is a punchline, and now I'm going to try to convince you that these objects exist and that these things can happen. So for that, I have to talk a bit about the time-like geodetic flow on Schwarzschild. Okay. Okay, so the first thing I want to say that we can split the geodesic into two families. Okay, they are what you can call, okay, for lack of better name, dispersive geodesics. Okay, so imagine that I don't know. This is like the event horizon. This is like the past. Okay. Then the dispersive, this is like the R equal. I don't want to draw Penrose diagrams because it doesn't capture R equal infinity in the way I want to for this time like geodetic. So these dispersive geodesics, okay, there are different versions. There are some that, so they are either connected to, H minus. So for instance, they can do something like this, okay? Or they can go from H minus to R equal infinity, or they can, emanate for M equal infinity and end up into the black holes. Okay, there are versions like this. Okay. And then the other set are bound geodesics or bound orbits. Okay. So what these ones do is that they oscillate between, I don't know, some smaller radius and a larger radius R1 and R2. Okay, so this is a geodesic, let's say gamma of t. Okay, and if you look at the radius of gamma of t, it sort of stay between some R1 that doesn't see the black hole and some R2 that doesn't see infinity. Okay, and contrary, let's say, to the null geodesic flow that many of you are maybe more familiar because it's linked to stability of black holes and waves. When you look at the this bound or this trap orbits, there's a very large family of them. It's sort of filled an open set in phase space. Okay. Okay. Yeah. Strictly less, not equal. And the other one also, they don't.
You're saying these are not the endpoints.
Not necessarily. Yes, if you wanted them to be the endpoint, then you can do that. Okay. 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 So the way you can, of course, do this is by looking at, you can remember that the flow is integrable. Okay. So if you introduce, I don't know, Ct, which will be like the killing thing. So this is d by dt. Ci, which will be like the killing fields, the three killing fields of generate the SO3 symmetry of Schwarzschild, then you know that for any geodesic that quantities like this, Ct, and also this, these are constants of motions along the flow. Okay. And let's call this the energy. So for signs, we put the -1. Okay. And okay, I will not look at the most general case. I will look in the case where the Vlasov fields are have also a spherical symmetry in the sense of Vlasov fields. It's not okay. It's a lifted symmetry. And so I don't need to know here everything, especially to classify the geodesics. I don't need to know everything about the angular momentums. I only need to know, let's say, the square of this sum over E from 3. So this I will call L squared. Okay, so this is angular momentum square, the total angular momentum square. We will say ecosymmetric, not the Vlasov field set. But what it means is that the Vlasov field F that I will consider, I can parameterize them as function of T, R, PR, and the total angular momentum. That would be enough to parameterize them. Okay. Okay. And now, so I want to keep that. So I will write it here so that I can keep this picture. So let me not, give you a full classification of all the time-like geodesic flow. Is relatively complicated. I mean, it's not completely trivial. Okay, so among other things that are conserved, of course, you have that the lengths of the vectors are concerned. Okay, and this is the same as saying that the energy is equal to PR squared plus some effective potential that depends on R. And the effective potential is just 1 minus 2m over R times 1 plus L squared over R squared. Okay. Okay, so let me introduce the set of parameters EL, okay, such that these are necessary conditions to get a bound orbit, okay? So I will call this the set A bound. So this is a set of E and L squared, okay? And the conditions that are E belongs to square root of 8 over 9, 1. I should say as well that there are some endpoints, which I will talk a little bit about it, where you are still, I'm excluding here, for example, the endpoint square root of 8 over 9. I will talk about this extensively later. These are also bound because they correspond to such stationary points of the flow, okay? You need L to be bigger than 12m squared. And then there is a condition that L must be sandwiched between two curves, one which will be the upper bound curve, and the other one which is the lower bound curves. Okay, I will tell you in a minute how you construct these curves. Okay, they are explicit, but they are a bit ugly. So I will not write them down. But I can draw a picture in the in the E. So this will be L squared, and this will be E. Okay, so I have square root of 8/9. Then I have 1. Okay, and then this curve LLB looks like this. Not 0 here. Here I have 12m squared. Okay, and the other curve look like this. So it has a different slope. Okay, and then it goes to infinity at 1. Okay, and this is the A bound is somewhere here. Okay, so sorry. Sorry, thank you. Better? Okay. So already I can tell you how it's going to be. Okay. The lack of regularity that you will see in the energy momentum tensor is connected to the fact that this picture is not like completely regular. Okay. Essentially, there are different boundaries in this to this region, and you will have different properties near the different boundaries. The lower bound here, no, sorry, the upper bound, okay, is actually good in the sense that if you look at what's going on near any of the point of the upper bound, you will find that things are relatively going well. For instance, the period of the orbits is goes to some extends continuously to any of these upper bound curves. The lower bound is bad, and the period, for instance, goes logarithmically. It's going to blow up. Okay, this point is really the worst point. Okay, in physics, this is called the innermost stable circular orbits. So it's sometimes called ISCO. And then what's going on at 1, especially near this point, so this is actually 16m squared. This is also bad, okay? And from what I could find in the literature, especially in the physics literature, but also in some, math things, this when you approach the good part, where things sort of the period is extends, sort of things smoothly, etc., this can be covered by previous things you can find. But the analysis near here, also near here, and near here, I think is had not been observed before. This is what we found. Okay, now let me just briefly tell you what are these curves. So this corresponds to, let me draw another picture. There'll be lots of pictures. Okay, so peak E and L squared in A bound. Okay, and then I will draw the effective potential in terms of R. Okay, and it looks like this. So you can see that the 2m, it has to go to 0, then it has a bump, and then it goes back to 1. Sorry, this one is really not the one I should draw. Okay, something like that. Okay, and there is another possibilities which can occur, which is that it goes like this, but the 1 is kind of above. Okay. The two different pictures are not so, the fact that there are two pictures is not so important, but for correctness. Okay. So in particular, so now if E is this range, what this means is that if you draw your E equal constant, so your energy curve, you should see 3 roots like this. Okay. So these three roots, I will label them as R0. So it's a function of E and L. And this is like R1. And this is like R2. Okay. And now the case where you reach LLB of E is when actually, for instance, in this picture, this would be, the E, and this will be a spatial potential that depends on E, which is VL of LLB of E. Okay. And if instead you were going to reach, which means that, okay, this lower, the LB stands for lower bound because it's the lower bound of L. Okay, but this is where you reached the top of the potential, not the bottom of the potential, because the behavior is very different. Okay. And if instead, like you, if this was LUB of E, then this means that you would be looking at a case where the energy is at the level of the bottom of your potential. Okay? Okay. So in particular, here you see, so this is E. Here you see three roots. This is kind of the regular case. Okay? And here you see two roots only, okay, which are either these two ones, okay, or it could also be, no, not this one, these two ones, or you could have, in that case, you have this one and this one. Okay, that roots. Okay, finally, the cases which are very bad is the case where E is equal to square root, this is the ISCO point, so this one and L equal 12m squared, I think. And in that case, you get one root, or if you get a triple root. So somehow I've also now been involved in, not even ODEs, just polynomials, but okay. There is also another funny case, which I will talk a bit less, but somehow the analysis is also interesting there, which is E equal 1 and L equals 16m squared, L squared. And this is actually one root, but for a different reason, because then the potential look then in that case, the polynomial, so the polynomial is really take this, okay, so it's really E squared minus VL of R. You can call this PR of E and L. Okay, and if you would please formally multiply this by, well, not formally, if you multiply this by R cube, then you get a polynomial of order 3. And this case is when the polynomial becomes not of order 3, but it degenerates to a polynomial of order 2. Okay. And then it looks like this. You get, this is 1. You never reach 1, I mean, it's asymptotically. And then you touch this point here. Okay. Now, if you look at okay, maybe it's a good time to talk about stationary Vlasov field. Okay, from that picture, you could ask, how could you construct a stationary Vlasov field? So it's not so complicated. You can do the following. You can choose B, which is compact, which is included compactly in A bound. So I don't forget how you write this, but something like that. Okay. So it doesn't touch the boundary of A bound in particular. So it's something that lies, I don't know, here. Okay. Now you would choose a profile phi. Just take any smooth function, which is we support in B. Okay, and then you would let f of R PR L squared to be equal to phi of E. Here E will be okay, you'll have to compute what E is in terms of the R in PR and L. Okay, and L squared. And because these are constant along the flow, then this gives you a stationary things, okay? So this is somehow related to some sort of folklore theorem in kinetic theory, which is Jean's theorem. I'm saying folklore because it's somehow believed to be true in many scenarios, but in some scenarios it's not really true as it's typically presented. So this is related to Jean's theorems, which is that in general, stationary solutions should be just functions of the invariant of the flow. Okay. However, if you look again here to this picture, you see that if you fix E and L squared, there are actually two orbits which are possible. There is an orbit which will go like this, and then there is the periodic orbit that goes like that. Okay. And if you only take a functional like this one, then it will have support on both orbits. However, these orbits are not good, and if you assume that you have this profile and you also keep this type of orbits, then if you compute the energy moment tensor or the particle number, total particle number, then it will be infinite. So it's not very good. So you have to exclude these ones. Okay, it will correspond to an infinite flux. Okay, which is logical because you imagine that these ones they go into the black hole. So something is feeding the black hole for all times. This is not possible. So to exclude them, then you just multiply by a cutoff that select this orbit. So for instance, since this is R0, if R is bigger than R0, then you don't see the one on the left. Okay. This cutoff, I claim you could even take it just to be a characteristic function of that set. And the reason why you could do that is because the transition from, let's say, 0 to 1 would occur in a region where the profile phi will be not be supported. You could arrange that to be true. Sorry. Okay, this is linked to the fact that since you choose B to be compact away from A bound, you never approach the top here. So you never approach really the transitions from this type of orbits to this type of orbits. And by compactness, you will have a gap. Okay. But the fact that you need to add these things, okay, this means that Jean theorems is not true in relativity. It is true, for instance, for Vlasov-Poisson in spherical symmetry. There's an old paper of Bat, Faltenbacher, and Horst that prove that. It's essentially just about proving that the gravitational potential is single weld. Roughly the proof. And this fact was first, let's say, highlighted and proven for the ancient Vlasov system. By Schaefer in a paper from 98. Okay. And like a different proof of this, also for the ancient Vlasov system, was given by Fatima. It's after a posteriori fact from one of the work she did in her thesis, so in 2021. Okay. Now it's a good time, since I already started, to talk about some literature on the subject and things which are related. Literature. Okay, so I won't be exhaustive, but I won't talk about the things which are most relevant here. So the most relevant one is a work by Renato Velozzo from his thesis. Okay, so this is 2024. So what he did is that he looked at F, okay, solution to the Vlasov equation, the linear Vlasov equation, again on Schwarzschild, linear on Schwarzschild, okay, not necessarily spherically symmetric in this work, which was C0 with compact support. And then he introduced a characteristic function of what? Of the dispersive orbits. So this just project F only on the orbits which are not trapped. Okay. So when you look now at f times this object, you can look at its energy momentum tensor, and Renato will tell you that this converges to 0 as t goes to infinity with some rates, okay, which depend how you approach infinity, in terms of u, v, r, etc. Okay. Okay. So d here is dispersive. Okay. Then there is another set of results which are tied to mixing. Okay, so this is a general belief in it's not a belief, but it can be proven in many situations in kinetic theory. So the mixing phenomena in general is that if you consider, let's say, F, we support only in let's say the trap or the bounded orbits, trap region, let's say, then we expect the energy momentum of F to relax to the energy momentum tensor of a stationary solution. Okay. So this goes back to work of Linden-Bell. This is supposedly true for Vlasov-Poisson and maybe ancient Vlasov and things like that from '62, and also work of Landau, which considers similar issues in the plasma physics case, but the equations are not the same exactly. But okay.
When you say Einstein Vlasov and stationary, you mean there's a common healing field for both?
Yes, it's the same d by dt.
Vlasov you consider them Schwarzschild. That's not the case, right? Schwarzschild has its standard healing field with rotational symmetry. And the Vlasov matrix construct has another.
No, it's the same. D by dt. It's a lift of d by dt to the tangent bundle because it's not. I'm French. In the Bourbaki sense, it's not the same. But oula. Okay. Okay, so then there are many works, so maybe I can add them here, about mixing, okay, which not necessarily, okay, I will just quote a few works, but I don't want to spend all my time on that. So I can quote, for instance, mixing without a rate, okay, which means that you have a type of relaxation of this form, but you don't know at which speed, and there is no, actual quantitative estimate. So this was done first by Riosseco and Sarbar. So they have several works. They have works that concern Schwarzschild. They have works that contain Kerr, in different situations. And this is also, really in the case where the support stays away from the boundary of this A-bound region. Okay. Okay. Then there are many other works by people connected to either Riosseco or Sarbar in this range. Okay. So there are also, for instance, mixing with a rate, but not for Schwarzschild, for some model problem involving trapping potentials and things like that. I will not go through all of this. There are also works about quantitative mixing. So this is quantitative by Chaturvedi and Jonathan Luke. So there is one from 2022 where they consider like a 1D model problem with a trapping potential, again staying away from the analog of the A-bound region. And then another one from 2024, which is more of a 3D model. So again, you have some sort of trapping potential. In this case, they look at linear quantitative mixings, but also the implication for nonlinear problems. So they also cook up a nonlinear problem for which they can show a long time existence compared to the the local existence that you could get. Okay, and then there are also several groups which also study both quantitative mixings and also like linearized ability including on a non-trivial stationary states. So when you look at the linearized equation on Schwarzschild, you get just the linear Vlasov equations, but you could linearize on a stationary solution, which is not Schwarzschild, which is close by to Schwarzschild. This gives you something more complicated. So these type of things were studied in particular. Let me not write all the names, but I will say them because they worked quite hard on this. Gunther, Rein, Straub. There is work by Ajik, Rein, and Schrecker. And there's a more recent one of Ajik and Schrecker from 2025, where in particular they study mixing when you approach the top boundary, okay, which corresponds to this elliptic point in the picture, okay, and where their analysis extends to this part. Okay. Finally, there are also many studies about the constructions of stationary solutions. Maybe I can put this here. Stationary solutions, okay. So in Vlasov Poisson, there are many things. I will not go through this literature. In the case of ancient Vlasov, there are also many things. I will only quote here the ones which are directly relevant to what's talking here, which is the initial work of Rein from 94, the work of Schaeffer, which I already mentioned here, from 98, and then the work of Fatima Jabiri. So she has one where she sort of looked at stationary solutions nearby Schwarzschild, starting from Schwarzschild. This one is from 2021. So this is Schwarzschild. And then she has another one where she studied this, but by perturbing Kerr. So this is stationary solutions which sort of deform Kerr. Okay. Having introduced all of this, now I can tell you. Yeah.
So the ones that you start with Schwarzschild, you obtain stationary coupled solutions.
This is ancient Vlasov, yes. Ancient Vlasov. Spherically symmetric, and this one is axisymmetric. Yeah. Yes. Okay. So what I want to do now is to imagine the following things. The reason why somehow I want to consider all these boundary points is because I see no reason why you should not. So if you imagine that you just take some profile in ENL, okay, and you just assume that your profile has a support near this point here, for instance, okay, you can cut this profile so that far away is sort of 0, but here it's just exactly a function of E and L squared. This gives you a perfectly smooth function of R, PR, and L squared. And there is no physical reason that I can think of to exclude those. Okay. So if you do this, where can I go? Maybe here. There's too many boards. I'm kind of lost. Actually, I should check this picture. This one is less useful. Okay, so take such an F, which is this property here. So we support, okay, containing, let's say, which is square root of 8/9 and 12 and squared. Okay, containing an open set around this. Huh? Open set around point, okay? And also assuming that when restricted to the A bound, so F restricted, let's say, to the bound orbits, as exactly this stationary looks like this. But then you need also this cutoff key R bigger than M. Okay? Then if you look at, F minus F restricted to the bound orbits, this is exactly the F restricted to the dispersive region that Renato studied Okay. So we know because of this that the T of the F must converge to the T of this F, let me call it F status stationary. And the question now is, can we sort of describe this object on the right? Okay, and so the theorem looks like that. So with F stats as on the left, let's say, you have that when you look at TF stats, so you can show that it is 0 for R less than 4m. It is C infinity on 4m 6m, which is already non-trivial because okay, of course you will have to look at why it's sort of there is an obstruction there, but because of this includes this lower boundary here where things are a priori when you look at the corresponding integrals, they look singular a little bit there. Okay. Okay, so in fact, it is C infinity on that set. And if you compute the derivatives at any order, they have limits of 6m and 4m. Okay, so it's really C infinity on the closure, if you want. Okay, it's also C infinity on 6m plus infinity, including 6m in the sense that if you take limits, I don't know, somewhere on the right of 6m, and then you take derivatives, sorry, on the right on 6m, and you mush that to the 6m, then you will find limits at any order. But there exist, let's say, F stats. Okay, it's actually it's a generic thing that also follow from the proof, but here I will state it only in this way, such that the limit as R goes to 6m, let's say minus, so this is R less than 6m, at derivatives. So it's also, first, it's also C0 everywhere. Okay, it's C0 on 2m plus infinity. Okay, so it's continuous. But if you look at, let's say, the first derivative of this, T F stat, on the right, it doesn't match, so d by dr, this is a function only of r, it doesn't match the limit on the left. Okay, so they don't agree. So it's not smooth in this sense. Okay, and the same is true as well near 4m. But with 4m, okay, you have to go depending on the 4m is a bit funny, which is that the regularity at 4m is tied to the decay of the field near infinity. So that's not obvious, but if you were to give me a profile which is compactly supported in the sense not in A band but in R, then it will actually be smooth at 4m. But if you have some tail, then it will not be smooth at 4m. Okay, so now I have maybe a couple of minutes to try to tell you about the proof of this. Okay. So there are a couple of key ingredients, but okay, you need some study of you could say fine, but I don't know. That's sort of fine properties or properties of the roots. Okay, of E squared minus VL of R. There is a relatively lengthy reduction of, let's say, this. So you view this as some form of integrals, and you work again and again to try to transform this to some sort of tractable integrals. Okay, which they will not necessarily be okay. Yeah, the integrand will not necessarily be always perfect, but you can find out whether they are singular or not. Okay, and here there's quite a lot also of monotonicity properties associated with either the roots or the polynomial that we monotonicity, which some of them I will mention to you. Okay, so let me try to do part of this reduction, and when I need the properties of the roots, I will essentially quote them, and you can believe me or not. Okay. So let's look at something like this. Okay. So it's an integral in P of the F stationary, okay, with some P weight and some measure depending on P. Okay, it will not be precise. And what you do with that, you rewrite them in terms of an integral in the energy and an integral with respect to the angular momentum L. Okay. So remember that everywhere F, where can I write that? F will be always equal to this cutoff times this profile. So here I have the cutoff, and then I have my profile. Okay, and then I have a volume form, and because of the change of a variable here, I have a mildly singular denominator, which is this one. Okay, so this cancels the roots of the turning points. Okay, so but okay, if you only had like these things with no boundaries to be approached, this sort of follows the analysis of this type of integrals by sort of classical type arguments in ODEs, Hamiltonian PDEs, like similar to computing periods in action angle variables. You'll find them relatively easy. Okay, so of course there is a condition for that square root to make sense, which is that E squared must be bigger than the potential. This, you can convert this into an upper bound for the maximum L allowed at fixed E. Okay, so you can rewrite this as an integral. Here in this cutoff, you remember that also, I forgot to say that, sorry, which is that, remember that I was taking some bump here near the ISCO point, and then I was projecting on a set of bound orbits. Okay, this means that I also multiply by the characteristic function of that set A bound. So here I have this cutoff, but I also have like a characteristic function of the set A bound. And this is a function only of E and L. Okay. So in particular, being in A bound means that E is restricted to square root of 8/9 and 1. So here I have this. Okay. Then I have an integral from 0 to L max. Then I have the two cutoffs, and then I have the profile dE dL. Sorry, and then I have the denominator. Okay. Okay. Now I'm asking myself. So in this cutoff here, there is also the fact that L must be above this curve, and this curve is LLB of E. Okay. So the question becomes whether this lower bound here is above this L max. If this is the case, then it doesn't contribute because it's n0, or whether it's below, and then I have this gives me a lower bound here. Okay, so the question becomes whether when do we have L max of E and R bigger than LLB of me? And the answer is if R is bigger than 6m, then let's call this, let's say, star. Then star holds if E, is equivalent to E is bigger than some minimal energy. And if R is less than 6m, then star is always true. Okay, so let me describe what is this lower energy bound. There is a lot of, there is many of these things throughout the proof. So you already see that there is some sort of asymmetry between 6m and the other part, but there will be more such things to come. So, okay, this is where I wanted to keep this picture here. Okay, so forget about the blue curve, doesn't matter. Okay, so this is an energy, okay, and this is a spatial potential. This is not any potential. This is potential where I choose the angular momentum to correspond to the lower boundary of this E. So this curve here, okay, which means that the energy sort of grazes the top of this potential. So here I have a double root, and here I have a single root, and this single root is R2 of E, okay, and E2 of R is the inverse of R2 of E. So this is the inverse. So it turned out that R2 of E is strictly increasing, which is not totally obvious. It's not R2 of E is not given by any tractable functions you could think of. And this is the inverse of R2 of E, which I claim is monotone. And it's actually monotone only for R bigger than 6m. So, okay, so why is this true? This I can explain relatively easily. Okay, I have it somewhere here. Okay, so imagine that you are looking at R on the right-hand side of 6m. So 6m will be somewhere here. Okay, and then what is this curve? The condition, this condition here, L max of ER is bigger than LB of E. This is the same as E squared is above the potential, but the spatial potential corresponding to this lower curve. Okay. So you look now at the picture and you say, this is the potential and this is E. Why do I need for this E to be above the potential? Well, I need R to be less than R2. Okay, and less than R2, using the inverse, this transfers into E bigger than E2. Okay. Okay. So I'm going a bit late, so let me try to rush off. So, okay, you do this a couple of times, this kind of a reduction. And then in the end, you sort of do also many, well, not many, but two of the change of variables in the integrals. And you reach a state where the integral looks like that. You have an integral. Let's say I'm looking only at R bigger than 6m, because you have to treat these two regions separately. Then the integral will look like this. This would be 1. Okay, then there will be a prefactor. This comes from some Jacobian in the change of variables. And finally, that prefactor has a power of 1/2, which is a bit worrisome because of typical square root lack of issues. And then there is the remainder of the integral in L, which now, after I've stretched using variable and things like that, will look like this. I have my profile. It depends still on E. And then it doesn't depend on L because I've used change of variables. It depends on some function L tilde, which I will not specify, that is a function of S, R, and E. Okay. And then it has a ds over square root of 1 minus S. Okay. The point is that this function is smooth. At least it's clear when you're away from any boundaries. Okay, so you could take derivative in R as many times of this. It doesn't matter. And this weight that you see here, okay, it's regular at s equals 0. It's singular at s equals 1, but it's just integrable at s equals 1. So you can differentiate this as many as a time. However, there's still this problem here because this object sort of vanishes. So there is a square root. Okay, it's sort of a complicated expression in terms of E. And it vanishes at one at the bottom. So you still have to be worried about that. Okay. This I claim that you can actually use as a change of variable in E. So there is still an integral in E. You can use this to define this as, let's say, P of E and R. Okay. You can use this as a change of variable in E to get rid essentially of that obstructions. But for that, you need that things to again be sort of monotone in E, which it is. So the important fact is that dP over dE is positive. Okay, for as a as a function, it's a you fix R bigger than 6m, then you can prove another monodicity property of that object here. Okay, but this lower bound sort of degenerates as E goes closer to square root of 8/9, which is an issue near square root of 8. Okay, and now okay, I'm lacking time, but so using these extra things, you can show the regularity, let's say, for any point R bigger than 6m. You still have to work for R equals 6m. And in fact, it's not, this is where we spend most of our time. And the idea to treat R equals 6m was to use another change of coordinates in E. But this change of coordinates in E, so we change it to E of Y. This was tied so that you could see something in the expressions here to really split this sort of polynomial in R and E as something tractable. Okay, so the way we found it is by looking essentially at the expressions that you have for LLB. In this expression, there are some specific square roots, and you try to you cannot linearize these square roots, but you can try to make them like fractional relations which are regular. Because one thing also I didn't mention is that this function LLB of E, okay, it's actually not a smooth function at this point. It's C1 1/2 near square root of 8/9. Okay, meaning that if you take the second derivative of this, it doesn't have a limit here. Okay, so let me not write down the change of coordinates E of Y, but what I can tell you is that if instead of looking at PRE, you write in another coordinate, which is X and Y, and here X is just R minus 6m, and Y is sort of the inverse of that thing, then you see something tractable because this sort of split into this object here. Just something like this, and then there is a denominator, but which is regular. Okay, so the denominator doesn't matter. And here you see just the product of two polynomials in Y and X, okay, where you can compute the roots explicitly and you can do all the computations you want because it's very easy. So that change of coordinates is magical, but makes things work. And so you can essentially rewrite this, a lot of complicated integrals, is an integral with respect to X, with respect to, okay, there is another change to do for Y, but we forget about this one for a minute. And then you get some sort of expression which look like an integral with some sort of kernel in X and S times some, something that still depends on the profile. And that kernel you can show, which is integrable with respect to S. This is an integral in S. And moreover, that the derivative of this kernel stay bounded, are still integrable, okay, with slightly different bounds. So you can close. Okay, on 6m, less than 6m, there's a similar analysis, which is not quite the same, but close, okay? And then near R equals 4m, again, there is a similar game to play, but which is a little bit different because the reason why 4m is tied to infinity has to do with the fact that there is the limiting profile look like this. It goes to here. This is 4m. Okay, and this is equal 1. Okay, so because of the fact that somehow the limiting profile, which this is really you cannot buy particles below 4m. Okay, this is connected to R equal infinity. Okay, I will not have time to talk about this, but thanks for your attention.
So, are there any questions?
So the fact that this matter distribution seems to have a jump, something like a jump of the level of the derivative, is this something that physicists have discovered before, discussed? Does it come up in other non-relativistic contexts?
As far as I know, I looked, okay, and I couldn't find anything like that in the physics literature. What you can find is that because they don't, okay, the reason I think it's because you have to look at these Vlasov things. The nonlinear version of this is I don't know at all what's going on, I should say, okay. What is known is that if you take like individual geodesics and you look what's going on near this point, then the physicists have some, from the fact that the period sort of blows up here, this is known. The fact that the period blows up here, this is known. We actually analyzing the period, we found that the period blows up here in a non-uniform manner, depending on the angle in which you do this. So for the people who like blowing up corners, you have to do a blow up of these corners. At least that's how we do it. And this also, I don't think had been seen by the physicists, for instance. As far as I looked and asked.
So, is there a conjecture for the rate that things would approach stationary state?
I don't have one.
Maybe Renato has the rates for if you don't have that, but yeah.
So if I don't stay close to the boundary,
he proved some rates. I'm wondering, but there are no conjectures for.
I have no conjecture about what's going on near this point. I think the next step I want to do is first whether to see whether this kind of even if you look at like the nonlinear Einstein-Vlasov but stationary, I do not know whether at the moment even the linear case, yeah, okay.
Maybe you avoid that point without the other. If you just mix something that's like
I see regular. This I think should be in the I think in the paper of Hajic and Schrecker, this should be there, but I don't remember the rates.
Okay, thanks.
It's finite. That I can remember that it's not like Landau damping where you can do it infinitely many times.
Is this the worst kind of sort of asymptotic singularity that you should expect? No.
No.
So what is the worst?
So the worst, okay, which is a work in progress, is that the problem is that here I'm looking at profile, large phi, okay, which where is the profile? I forgot, I wrote it somewhere. But the function f, was this profile times some cutoff, okay? And all the singular part came from this cutoff. But you could ask the following, okay, here I justified that this was a good thing by saying that you can generate those by looking at the dynamical problem. But now what if you start with a solution which is not stationary in the trap region, okay? What kind of stationary profile should you expect it generates? And the fact that the periods blows up at various parts lead me to believe that this stationary profile will not be smooth in ENL. And so my early computation suggests that the smoothness on the right side and the smoothness on the left side is destroyed in that picture, and that you get C4 1/2 regularity. Okay, okay, this is work in progress. I still have to check a few things. I think it's correct, but okay, we'll see.
Any final questions? If not,